Hola, chaps. Let's learn. Hola, chaps. Mr. Turek here. This is for chemistry and a review for physics as well. The heating curve, the graph that you would generate when you ask yourself, what is the temperature of a substance as I add more and more energy to it? So down at the very bottom of the curve is solid material. And absolute zero on the Kelvin scale is defined as that temperature at which all motion stops completely. Kinetic energy average of a substance goes to zero. Even the electrons orbiting it are stopped in their orbits. So that's pretty cold. We can't get there, but we've gotten close to it in our laboratories. What I've sketched here is the generic heating curve that says when you're really low in temperature, you are in a solid state. And there is a quantity that we use. Of course, we can always come up with equations and formulas. There's a quantity that we can use that express how much heat energy we add to a substance that leads to the resulting change in temperature for that substance. So here's a generic curve, somewhat generic. It's somewhat suggestive of water in particular. So in the solid state, water can go down to absolute zero. And I should mark this as being in the solid state, right? Well, if I keep adding heat energy to it, which is what I'm doing on this bottom graph, so you could think of it as like putting it on a hot plate and having it just stay on the hot plate for a long time. So starting at absolute zero, as I add heat energy to solid ice, it becomes hot ice, meaning it might be at 100 degrees below zero on the Celsius scale. And as I add heat to it, now it becomes negative 50 degrees on the Celsius scale, negative 20 degrees. So its temperature is increasing. It's still below zero on the Celsius scale, and I want to just use the Celsius scale from now on for this talk. It's still below zero, but it is becoming warmer. Now, when I use the phrase hot ice, I mean that humorously because hot ice is a colloquial expression that means you have stolen diamonds. But I have students who miscalculate heat energy in this section of the course. They say, well, if I start with ice and I add 1,000 joules to this one little gram of ice, the ice will end up at a temperature, whatever it is, 500 degrees Celsius. Well, that's hot ice, but it can't actually exist under standard temperature and pressure conditions. Here's what happens instead. Once the ice gets to a certain temperature, the solid crystalline structure of the ice being held together by van der Waals forces and hmm, molecular cohesiveness and stuff I haven't really explained to you, then they break apart. Well, that is a transformation of potential energy, chemical potential energy. So solid ice has very low kinetic energy and very low potential energy at the same time. It's a crystalline structure. The molecules are vibrating a little bit in place. The colder the temperature, the less they vibrate. Add more heat, they vibrate a bit more. Add more heat, they vibrate a bit more. But there comes a point, the freezing point slash melting point for that substance, at which when you add more heat energy to it, it actually lets it melt and change from a solid, sometimes crystalline structure, into a liquid structure. So the heating curve for water is theoretically under standard temperature and pressure at 0 degrees on the Celsius scale, which is 273.15 Kelvin. Okay, so it's also 32 degrees on the Fahrenheit scale, but that's TMI, right? So as I add heat energy to solid substances, we define that as melting the substance. And what I'm doing is I'm adding heat energy, but it's not changing the temperature. it's changing the potential energy of the substance, breaking it apart from being in rigid rows and layers, like a crystalline structure, into something where the atoms can slide against each other. So a liquid has a definite volume, but not a definite shape. And it took energy to break apart, well, to increase the potential energy of that solid to the point where molecules or atoms for some substances could start to slide against each other. Then it's in a liquid state. What happens when I add more energy to it? Well, the temperature increases. And I've changed the slope here to emphasize that it might not increase at the same rate. In fact, for water, the rate at which solid ice heats up is indeed different from the rate at which liquid water heats up. And they may have done this backwards, but solid compared to liquid changes almost by a factor of two different in its slope. Here it's around 4 joules. Oh, is that right? 4 calories or so per gram, 4 joules per gram, something. Here it's only two. So I think I did the slope correctly after all, right? So this is around a slope of 2. This is around a slope of 4 if we put it to a scale with the units on it and all that stuff. But what happens when I heat water? Well, as I heat it, it gets hotter and hotter and hotter. But there comes a point at standard temperature pressure at which it will no longer become hotter as liquid water. We call that the point of vaporization. You would call it the boiling point for water, but this is a chemistry course. We have to use fancier words on occasion, give you some vocabulary to struggle with learning. So vaporization is changing from a liquid to, well, what do you get? We're adding energy, but we're not changing the temperature. We're changing the potential energy again. So in liquid water, we had these molecules or atoms, and they're free to slide around each other. They have definite volume, but indefinite shape. When I add even more heat energy to that, it breaks apart the potential, it increases the potential energy so that those molecules or atoms can now fly apart from each other. It takes energy to do that, and it doesn't change the temperature. But once I have added enough energy to transform it into this indefinite volume, indefinite um, shape, we call that the gas phase. And at that point, if I continue adding heat energy to it, its temperature continues to rise. And that slope can be different from the other two slopes. In fact, for the situation of water, the specific heat of the gas phase of water is similar, quite close to, but not the same as the slope for solid water, ice. And I didn't look it up to see which one is slightly steeper. That's something left as an exercise for the interested reader. So, starting with a solid, add energy, it becomes hot, but only to the point at which it transforms its physical state from a solid to a liquid by melting. I can heat a liquid, but not indefinitely, only to the point at which it begins to transform from a liquid into a gas. And we call that boiling for water or vaporization. And then I can heat the gas, and eventually, yes, you can say there's a fourth state of matter where it becomes a plasma. We don't care about that in this course. Coming down the curve, if I start with, let's say, water in the gaseous state, so steam, as you tend to call it, if I keep removing energy from it, its temperature becomes colder and colder and colder. But it's not going to become cold steam as you would think of, oh man, I touched that steam, it's really cold. What will happen is that when it gets down to this point of vaporization, it will condense. So when it goes from a gas state to a liquid state, we call that condensation. And no matter which way you're going up here on this little plateau, this is called the heat of vaporization. Okay, so that's the name for the quantity that we associate it with this plateau for a given substance. So in the case of water, for example, the heat of vaporization is some number that we would look up on our reference sheet. As we continue removing heat energy from it, it would condense from a gas into a liquid. As a liquid, it would cool down, cool, 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 but not become cold water as in below the freezing point of water. When it gets to its freezing point, it freezes. So when we're going this way on the curve, you would call it melting. When it is going from solid to liquid, we call it freezing when it goes from liquid to solid. And just as we have a term called heat of vaporization, here we have a term called heat of, but no, we don't call it heat of melting. We call it heat of fusion. It is a different valued constant from the other one. So heat of fusion is specifically used for calculating how much energy is involved in transforming a given substance between its solid and liquid states, whether you're going in the melting direction or in the freezing direction. And then, continuing down the curve, yes, we can just continue removing heat energy from solid water. So you can take ice and make it colder and colder and colder if you have the technical means of removing heat energy from it. So making ice cold is the process of taking heat away from it. And this leads to something that the students sometimes don't think through. But what if I started with cold ice and I put it in a glass of water? The ice would be absorbing heat from the liquid water, causing the ice to become warmer. And when it gets to its melting point, it will melt. So, ice melting is solid water that is absorbing heat energy. Sometimes you think of it as, oh, the ice is giving off coldness, but that's not the correct way to think of it. The right way to think of it is solid ice is absorbing heat energy as it melts. And as a result of absorbing the heat energy, it melts. I guess that's a good way to put it. All right, so I should have challenged you with drawing this curve on your own. What do you expect the heating curve looks like for something like water? Well, maybe you didn't have enough guidance for me in the first place that you could have drawn it. So here's the answer. This is what a generic heating curve looks like to transform a solid into a liquid, into a gas, and then back down the heating curve. For some substances, the slopes would be different values. The plateaus would be at different values. So for gold, it doesn't melt at 0 degrees Celsius. It melts at a much higher temperature. It's there are terms that go with the slopes of each one of these. I didn't mention them uh, specifically, but now I should, right? So the slope on the solid curve is called the specific heat. The slope on the liquid curve is called the specific heat. And the slope on the gaseous curve is called the specific heat. So they're all called the specific heat, which means how much heat energy does it take, and you have to specify the units, to increase the temperature of that substance by a given amount of degrees. So I should pull out an example, but off the top of my head, the specific heat of liquid water is 1 calorie per gram for liquid water. Meaning, if I had 5 grams of water and I wanted to increase its temperature by 1 degree, then I would have to add 5 calories of heat energy to that quantity of water. So there's an equation for it. Gee, I wasn't going to go this far, but what the heck? You're advanced students, you're ready for this. Q is the amount of energy that a substance has. And the units are either calories, as in chemistry class, or joules, as in physics class. Okay, so it could be in either one of those units, and there is a conversion that goes back and forth thanks to the son of a beer brewer. All right, so Q is the equation for energy. M is the mass of the substance, and you should be careful because it could be in grams, often is, but what if it's in kilograms? Of course, you know the conversion because you had to memorize it from the beginning of the school year, that 1 kilogram is equal to 1,000 grams. So anytime that it's in one unit, convert it to the other as necessary. And then for specific heat, what symbol should we use for it? Often the symbol that is used is the letter C, and then we would add a little subscript. So if it's solid, then, that would be S, right? So solid, specific, heat, and then you have to worry about what are the correct units for it. So in the units that deal with calories, you have to have the specific heat in the matching units, and the units that deal with joules, you have to deal with the specific heat in the matching units of joules. So there's the specific heat of the solid, the specific heat of the liquid, and the specific heat of the gas. The equation becomes the amount of heat energy that a substance has is the product of the mass of the substance times its specific heat, and you have to realize, okay, that's different from a gas than it is for a liquid than it is for a solid. So you need to be very specific about what phase state you're talking about. Are you talking about liquid water? That's 1 calorie per gram. Okay, we'll use that as an example. Times the change in temperature. So I remind you, delta means change. And you should work in consistent temperature units here as well. Degrees Celsius is something we would use quite often. The Kelvin scale is an offset from the Celsius scale by a fixed amount, 273.15. So example here, the one that I said verbally, let's just do it again. Suppose I have 5 grams of liquid water, and I say its initial temperature is 15 degrees Celsius, and I add 30 calories of heat to it, knowing that the specific heat, here I wrote S, that's supposed to be an L, isn't it? Okay, specific heat of liquid. Yeah, I know, you would have gotten extra credit if you told me. So for water in particular, the specific heat of liquid water is 1 calorie per gram per degree Celsius, but it also works out per Kelvin, the same unit, because a change of 1 degree Celsius is identical to a change of 1 Kelvin. So either units, just pick a unit and work with that one. So back to my example. If I had 5 grams of liquid water and it's initially at a temperature of 15 degrees, and I add 30 calories of heat energy to that water, the apparent question is, so what will be the final temperature of that water? Yeah. Pause, figure it out. I'm just going to keep going. So using this equation, I would go 5 grams times, 30 calories is equal to 5 grams times 1 calorie per gram per degree C times the change in temperature. So excuse my poor math, but solving for delta T, I have 30 divided by 5 is 6. So the change in temperature will be an increase of 6 degrees Celsius. And last step, if I start at a temperature of 15 degrees and I increase my temperature by 6 degrees, here's another way of expressing change in temperature. Change in temperature is defined as your final temperature minus your initial temperature. So when you rearrange that, that means the final temperature is equal to the initial temperature plus the change in temperature. And don't forget, this can be positive or negative. The temperature can go up or down, increase or decrease. In this particular problem, you can do this one in your head, right? And I get 15 degrees initial temperature plus an increase of 6 degrees Celsius means my final temperature is 21 degrees Celsius for all 5 grams of that water in this example. Okay, as exciting as this is, as beautiful as the theoretical curve is, now I want to share with you something that didn't work out quite perfectly. So I went outside. I used a hot plate from school that I brought home. I put a beaker on it. I put some ice in it. I added a thermal probe, and I set it to record the temperature every 6 seconds for 25 minutes, starting with cold ice out of my freezer. I put it on a hot plate for 3 minutes and let it just sort of settle. The thermal probe measuring, okay, so here's the temperature of that substance. Then I turned on the hot plate and let it run for the rest of its 25 minutes, recording data. The video, I shut it off and turned it back on so you didn't have to watch the ice transform for all 25 minutes, but this is part of the video right now. So sadly, it didn't work out quite as perfect as this drawing that I just shared with you. But nonetheless, when you do calculations for these science courses, pretend that it's this beautiful, perfect curve like I've just shared with you, that all the solid melts before the temperature increases, that all the liquid converts to gas before the temperature increases. Unlike what the rest of this little video clip looks like that I'm now going to append to this. All right. Ciao. Continued.
Hola chaps, Mr. Turk here. I'm going to attempt to boil water. But of course, I'm not going to make it that simple. That's too easy. So what I have set up here is a hot plate, a temperature probe that's meant to dangle just above the bottom of the glass beaker that will end up sitting on the hot plate, a cup of ice that will go into the beaker after I measure, well, the mass of the empty beaker and then the mass of the ice in the beaker. All this with data to be collected by Logger Pro, which is currently reading the ambient temperature as being 29.0 degrees Celsius. Right, so here we go. I've set it so it's going to sample once every 6 seconds for 25 minutes, and we kind of need to get a baseline established, so let's wish us some luck. First step, I'm going to put the empty beaker on the electronic balance, and this time, just like my first attempt, it's recording a value of 97 grams for this empty beaker. Step 2, I'm going to add ice to this beaker. And really I need 2 hands to do this, so forgive me while I go and grab it and fill it with ice as best I can. And read the new value. There it is, filled with lots of ice. And it's reading the value of 256 grams. Alright, next step, I'm going to put this on top of the hot plate, which is currently shut off, with the thermal probe jammed into the beaker. And of course it can't touch the bottom of the beaker, it's just dangling at a certain height above the base. And I'm going to start data collection right now. So immediately the temperature dropped from 29 degrees down to 1.4 degrees Celsius. Now it's gone below zero, negative 1.3 degrees C, which is logical because ice is typically stored not at 0 degrees but below freezing in a freezer. So the fact that the temperature is dropping down below 0 degrees is not at all unexpected. I want the temperature to try to stabilize here before I turn on the hot plate. So I am going to wait until the curve becomes somewhat level before doing the next step. And while waiting for that to occur, I don't have much to share with you. This is outdoors, it's a sunny day, it's a lot hotter where you are than where I am. And you can see that the curve is leveling off already, particularly if I zoom in. I don't know if this is focusing for you well enough for you to read it, but I'm dictating it to you, narrating it. It says it's leveling off at about negative 7.5 degrees Celsius, plus or minus. Now I'm going to wait, so it's been a full minute for it to somewhat stabilize. I'm going to wait till we get to about 2 minutes. Right now we're at 1.4 minutes. So every 6 seconds is a tenth of a minute. Here we're at 1.5 minutes in terms of data collection. I doubt you can read the values. And of course, I'm going to shut this off and switch out batteries. Here we go. You now have a feel for how long it takes me to switch out batteries. It now reads 2.8 minutes. Temperature's climbing a little bit, and so what I'm going to do is choose to, at exactly 3 minutes, I'm going to turn the hot plate on to high. So here it is, 3 minutes, and I'm turning on the hot plate and setting it to its highest temperature. So it will now begin to heat up. You can see that some of the solid ice is already beginning to transform from its solid state into a liquid state, and the graph is collecting data. There's really no need for me to record the entire 25 minutes of time that I designated for this thing to run, but I wanted you to see the beginning of this at least. So had to switch batteries for less than 1 minute of time approximately, and now we're at 3.6 minutes into this experiment. The temperature is currently reading 6 degrees below zero on the Celsius scale, and the hot plate is heating. The little indicator light says it's heating up. It takes this hot plate a finite amount of time to respond to the command to turn it on or off, and I don't know how much time that is, but the experiment is underway. It's a steady rate of increase of temperature on the thermal probe, which is interesting. It's as if the hot plate has not yet begun to do its job, because try to remember, I did not turn the hot plate on until we got to the 3 minute mark, and right now we're at 4.4 minute data point. So the temperature graph is not yet displaying the effect of turning on the hot plate. And I see if I don't separate the electrical cords from the hot plate, I'm going to have another interesting experiment taking place, intentionally or not. So at 4.8 minutes, temperature is currently negative 4.9 degrees. 4.9 minutes, negative 4.8 degrees Celsius. Let's see what it's at 5 minutes. It's at negative 4.7. So it's still increasing at a steady rate. And I'm going to go ahead and shut this video off for now and let the experiment unfold over the next 25 minutes of data collection. So just an overview of the whole thing. I've taken an empty glass beaker that had a mass of 97 grams, and I added water to that beaker until the total mass of beaker with ice in it was 256 grams. I left that on the hot plate shut off for the first 3 minutes of time. And you can see that the temperature probe quickly dropped from ambient temperature, which was about 29 degrees Celsius, down to a minimum below negative 7 degrees Celsius. At 3 minutes into this experiment, after I started collecting data, I should say, I turned on the hot plate at full power, and now at the 6-minute mark we're beginning to see evidence that the hot plate is heating up. With my hand I can feel some heat from the hot plate, but for now I'm going to let this experiment run its course. Alright, here we go. We're at 13.5 minutes into this experiment, and I wanted to turn the camera on for a moment and prove to you that there's still some ice left in the container right now. And as I show you the graph, you're going to say, what is going on? What is going on? I can tell you as the person standing here that every major change to the trend of the graph corresponded to a shifting of the ice that was still in the beaker. So as it repositioned itself, it would also have an effect on the temperature readings. So right now I can still visually see there's a little bit of ice that's behind the temperature probe as I look down into this beaker, and it's rapidly shrinking before my eyes, but it's still present. The temperature probe, you should be able to see, is well above the bottom of the glass beaker. It's well immersed in the water. Although this beaker was filled to the rim with ice and air, you can see that when it converts to liquid, it's a measly 150 or so milliliters of liquid water. The graph is continuing to go up. We're at, well, in 5 seconds. Mark, we're at 15 minutes into this experiment. I set it to go for only 25 minutes. The temperature is 34.5 degrees Celsius, and the very last of the ice is just melting now. We're coming up at 20 minutes into this experiment. You might be able to see that there's some convection taking place. All the water is now in liquid form in this container, but when you look at the graph, here we're at 20.1 minutes, it does look a little squirrely. Well, this is the way it's going. And also note that the computer has auto rescaled the vertical axis because the temperature is now 86.4 degrees. That would not have fit on the original y-axis scale, so it's rescaled things down accordingly. We're at 20.5 minutes and a temperature of 88.6 degrees. You can see some bubbling beginning on the side of the beaker. Possibly hear it. Alright, so only 4 minutes left in this experiment. Mark, we're at 24 minutes into this experiment. You can see the gas bubbles rising, signifying that this is boiling water at this time. And what, pray tell, is the graph doing? Well, the graph increased rapidly after the ice melted, and now it has reached a plateau. It has stopped increasing. It's hovering around 98 point something degrees. 30 seconds left in data collection. And what you can see is even though the temperature had steadily increased for some period of time, it's reached a plateau, and the water is not going to go above the boiling point of water under these conditions, which is more or less sea level on this warm sunny day. And Mark, 25 minutes, this ends data collection. I'm going to now shut off the hot plate. It'll take the water some time to cool down. I'm not recording past this point with the data collection equipment. I set it to only go for 25 minutes. It's been that amount of time. This will be the graph that I refer to as I discuss with you what happens when you try to melt ice and boil water. Some of the things that we can get out of this graph is the energy output of the hot plate, at least the extent to which it was transferred into the beaker, and some information about the phase change that takes place as the water boils, and an attempt to explain this first part of the graph, for the first 15 minutes, I remind you, there was still ice in the container. Small amounts were still there at about the 15-minute mark. Alright, this concludes this part of the video for now. There is one more measurement I'd like to carry out before I take this completely apart. So I had shut the hot plate off perhaps 5 to 7 minutes ago. It's starting to cool down. I'm removing the thermal probe. Need a third hand. Okay, this is too hot to handle, but what I'm going to do is use a pair of pot holders and put it on the electronic balance and see what is the current mass. I remind you that previously I had measured 256 grams, and what will it read now? All I've done is turn ice into water, you say, but is that all that I had done? So the result is currently reading 230 grams of water, and of course, as a chemistry student, or physics student even, I would expect you to be able to account for the difference between the initial mass of beaker with ice and the final mass of beaker with water. Where did the missing mass go?